We have already seen how the projection of a circular motion with constant speed is a simple harmonic motion. There's another important case of simple harmonic motion. Consider a pendulum of length L with a bob of mass m. The string is massless in our case. We call this the simple pendulum. We want to describe the oscillatory motion of this pendulum. For that, I will draw the free body diagram where the forces on the bob are the force of gravity and the tension from the string. I will write Newton's second law for this bob, but instead of using the x and y axis, I will consider the axis tangent to the direction of motion and the perpendicular to that, which is the direction of the pendulum itself, the string. Now let me write Newton's second law for rotation, that is, the equation of the torque. The torque is the vector position cross product the force. The distance of the bob to the fulcrum is L, and for the cross product we have to project the force of gravity in the direction of motion. mg times the sine of the angle theta. This, of course, will change with the motion of the bob, so it will depend on the angle through the sine of theta. The moment of inertia of the bob about the fulcrum of the pendulum is m times L squared. The change in theta is just the angular frequency, but be careful because it's pointing in the other direction. When theta decreases, omega increases, and when theta increases, omega decreases. Therefore, a negative sign. So I have this differential equation for the motion of the simple pendulum. This is a non-trivial equation to solve, for which we might want to do some numerical calculations with a computer. But what happens if the oscillations are small? Well, for small oscillations about the equilibrium position, we can expand the sine function in a series of Taylor. The sine of theta about the theta equals to 0 is the sine of 0 plus the derivative of the sine of theta evaluated at 0 times theta plus 1/2 of the second derivative evaluated at 0 times theta squared, and so on. For small angles, we can neglect the higher order terms, orders that are higher than 1, so we can approximate the sine of theta as theta itself. This only works for small angles. Now, this new differential equation is much simpler to solve. As a matter of fact, it's an acquaintance of ours. The second derivative of the angular position is equal to minus a constant times the angular position. We already know that the solution to this differential equation is a trigonometric function. Theta equals to theta naught times the sine of omega times t plus phi, the equation of a simple harmonic oscillator. You can check that this will have an angular frequency of square root of g over L and a period of 2 pi times the square root of L over g. So the period of the oscillations of a simple pendulum is given by the length of the pendulum and, of course, the gravity of the planet where you are. With this, you know now how to tune a grandfather's clock with a long pendulum. If you have the chance to have one of them, you can see how at the bottom of the bob there is a tiny bolt that allows you to move slightly the bob up or down. By doing this, you can change a bit the period of the oscillations and make it go at the right pace. You can also see that those pendulums are moving in this small angle regime. Of course, this is an approximation, but a very good one. May science be with you.